Okay, it's my great pleasure to introduce today's colloquium speaker, Chung-Pei Ma. She received both her undergrad and graduate degree at MIT, after which she went to Caltech as a Prize Fairchild postdoctoral fellow. After that, she was assistant faculty and associate faculty at University of Penn, after which she then moved to UC Berkeley, where she's been at since 2002. So Chung-Pei is a theoretical cosmologist and theoretical astrophysicist, and she studies various aspects of the dark and lumpy universe. So she studies various aspects of dark matter, the growth of structure, as well as supermassive black holes, which we will discuss today, and lumpy universe in terms of how, from the very smooth conditions, the structures as we know it arose as a function of time. So it's a great pleasure to have her here today about supermassive black holes and nearby galaxies, including observations. I hear that's right.
Thank you, Miriam.
The lights down? Okay.
And thanks for the invitation. Yes, I'll be primarily talking about an observational project that I initiated about 5 years ago. I won't go through the motivation so much behind it in terms of the theoretical work, but it was motivated by certain simulations we were performing at that time, trying to understand how to form the most massive galaxies and their central black holes. And during that process, we were making certain predictions that I was curious to check out, and then that's when I realized that data back then were quite sparse, and that motivated me to initiate this observational work. And I would like to highlight the contribution from my former PhD student, Nicholas McConnell. And then on the left side, these are collaborators mainly who have worked on the black hole part of the project. And now we have an ongoing survey called the Massive Survey of nearby the most massive galaxies. And Jenny Green, I would like to highlight her collaboration here. She's instrumental for for moving this survey forward. But I'll mostly be focusing on the black hole part of our work. So let me start out with some motivation for why we will want to study black holes in the most massive galaxies in the nearby universe. First of all, let's just think about where are astrophysical black holes found. The probably more mundane version, ironically, is actually the end states of massive stars. Black hole is one of the three graveyards of stellar evolution for very massive stars. They die, they're extravagant, they spend their energy very rapidly, they die spectacularly. And I won't go into the details here. There's some good candidates, but typically they are in the range of tens of solar masses. And Miriam is one of the world's experts on studying the end products of these massive stars, the supernovae and black hole and a gamma ray burst and so on, and various things. So I won't go into the details here. But I would like to focus on sort of the other category of astrophysical black holes, and they're called the supermassive black holes, in contrast to just a mere 20 solar masses, which are the most massive stars. And these black holes tended to be found at the centers of galaxies. And the best known case is the one in our own galactic center. And this is an infrared image of our own Milky Way. And the estimated mass for that black hole is about 4 million solar masses. And this is actually at the very low end of the supermassive black holes we know of. Today I would like to talk about those that have masses between 1 to 10 billion solar masses.
Where was this photograph taken from?
That's a Kobe image in the infrared of a derby image. Okay, so you can look again in the infrared. You want to look through the dust is attenuating the optical light significantly. So in the infrared allows you to look much deeper. And this is Andrea Ghez's group at UCLA. Of the very crowded stellar field towards our galactic center. And without the arrow, you probably wouldn't know where the center is, but that's where the Sagittarius A star is. Again, I don't want to go into the details. This has been observed very much, the active environment around this part. And I just want to highlight about 2 decades of work based on her group and Reinhard Genzel's group that are actually able to map the individual stellar orbits at the very center part of our the center of our galaxy. And by using these orbits, remember this is in projection, okay? They're able to infer the mass, how the 4 million solar mass is determined. This is the only galaxy for which we can actually resolve individual stellar orbits because it's only 8 kiloparsecs away, 25,000 light years. Okay, when we want to look at other galaxies, they are so distant that there's no hope that we can actually resolve individual stars. So in that case, we study them statistically. You want some kind of tracer, either stars, luminous tracer, gas, masers, that's very, very close to the black hole, and you use the velocity distributions of the stars and trying to probe the central mass. Okay. So this is the best known supermassive black hole in the universe, but there are many pieces of evidence pointing towards active galactic nuclei. Okay, that something is in there, seems to be swallowing up huge amount of gas, and then accelerating particles to very high energies and emitting jets and radial lobes. And some of these are known as active galaxies. The most luminous type of those are known as quasars. And this is M87 nearby, the most sort of prominent galaxy in the Berkeley cluster, Messier object 87. And this black hole is inferred to be about 6 billion solar masses. Okay? And there's just some extragalactic examples of activities at the centers of galaxies. And then there's another example of, now there are a few examples of not just a single black hole, but possibly a binary black hole. And this most famous case is probably NGC 6040, a fairly irregular looking galaxy in the optical. And if you zoom into the center, these are Chandra X-ray images of the central parts. And it seems to show 2 distinct emitting areas being interpreted as perhaps 2 black holes. The distances here is a few kiloparsecs, so they're by no means quite merged yet. But the various studies have shown that when you have 2 black holes so close, perhaps brought together by the mergers that put together this galaxy, okay, they sink through dynamical friction. They start to form a binary at the gravitational center of the gravitational potential. And of course, you would like to lose a lot of orbital energy for them to merge further. And they begin by kicking out stars. And then there's question about whether you can merge them to the final parsecs, therefore coalesce them and form a bigger single black hole. During that process, of course, one of the most interesting results will be gravity waves coming from the very final spiral of these objects. So I just want to use this to showcase that there may be binary black holes out there that will have strong implications for gravity waves, not for the LIGO frequencies, but rather for LISA, or I'll talk very briefly about the pulsar timing arrays that are sensitive to these low frequency astrophysical sources. Okay. And then let me now briefly highlight one interesting fact about these black holes. Okay, I'll talk about how to measure the masses in a little bit more detail in a second. But from whatever mass estimators we can find, from light emitting things very close to the hole, over the past few decades, this correlation had emerged that the black hole mass seems to be positively correlated with whatever parameter you use to estimate the size of a galaxy. Okay, whether it's the mass of the bulge of the galaxy, or the velocity dispersion, or luminosity. This is a cartoon picture. It's looking very nice and neat. I'll show you the current data momentarily. Basically, bigger galaxies seem to host bigger black holes with significant scatter. But now we have measurements over 4 decks in mass. So this positive trend is definitely there. So this has caused a lot of excitement because this is telling us somehow the growth, the formation and the growth of black holes, which is at the very center of these galaxies, seems to know about the environment it lives in. There is a positive correlation. Therefore, the black hole formation, galaxy formation seem to be intimately linked. And that made people who study galaxy formation very excited too, because we would like to understand how this positive correlation was established and whether this is preserved over the cosmic history. Okay.
Is it understood why supermassive black holes are in the center of their galaxies?
They're partially. So galaxies are mostly primarily put together through mergers. They were smaller initially, and then they come together to form bigger ones. So during that process is understood fairly well when you merge galaxies, and you can do this fairly easily and using numerical simulations these days. The central masses will come through because they lose energy and angular momentum through dynamical friction. And they will invariably sink to the center. How fast that happens is another story. How you see the very initial black hole is another big question. Whether they grew out of the stellar mass black holes somehow, or they collapse in one cluster of 10 to the 5, 10 to the 6 solar masses, and so on, that's still undetermined.
Do you have any idea if there's another black hole around Sagittarius A, a much smaller one? Like how well is that?
Yeah, there are strong constraints on that. I think there is no obvious sign for that. I think that would have perturbed some of these orbits. But again, all these statements only is valid for some region, right? You can always hide something very close to it. But then the question is stability. How do you actually make the two stable for a long time without merging them? Okay, so this is, again, I'll show you the data momentarily, but let me now say a bit more about black hole masses. How do we weigh black holes? Okay, and there are, other than the very local ones, so the Milky Way is the best example, right? We're using stellar orbits to basically Kepler's law, okay, to infer the black hole. Otherwise, you can use stars collectively. It's like a swarm of bees. Okay, when they're far away, you can't see individual bees, but I can measure the velocity distribution from the collection of bees, and that will still give me a lot of information about the central mass. And I just want to highlight the importance of the local black hole mass measurements, which is the focus of my talk. Local meaning, within the local hundreds of millions of light years versus high redshift. Okay, the reason is this really pins the black hole distance ladder. So I would like to draw an analogy to the very familiar cosmic distance ladder. We all know that you start out, you need very good foundation, and all higher rungs of the ladder depends on calibrations to the lowest one. Okay, there are always some unknown parameters that you need to calibrate to this lowest run. So it's very important to get the nearby stars right, or galaxies right here. Similarly, for black hole mass measurements, we would like to know, in addition to nearby galaxies, quasars. Quasars have been found to redshift of 5 or 6 when the universe was very young. They seem to be hosting a range. I mean, their luminosity is believed to be powered by a central, very active galaxy that's gobbling up lots of gas. Okay. So quasar is a very active phase of a galaxy, but to infer their central engine's mass, people use various secondary or indirect methods, for example, reverberation mapping for active galactic nuclei. The more distant quasars using some kind of emission line width. Okay, I don't want to go into details here, but all these measurements have an unknown coefficient that is calibrated to the local black hole mass galaxy property. So that normalization is critical for moving to the past history of these black holes. So it would be very useful to get this very local measurements as well as we can. And let me just now highlight some results from these higher redshift quasars. Okay, again, quasars are a very special population of galaxies. And this is a Sloan compilation of quasars from today, redshift 0, out to the high redshift universe. That's a function of look-back time here. And again, these black hole masses were inferred from emission lines of carbon-4 or so on. So they are quite uncertain, okay, probably up to a factor of a few. But the power of this kind of study is the statistics. So here you're seeing thousands of dots from fantastic Sloan quasar spectra. Okay, so they may overall be offset by something, but it's dramatic to see this cosmic decrease called downsizing of black hole masses, of the masses of black holes that live in the quasar environment. Okay, so again, if you read the axes here, at high redshift, some of these black holes may have already reached 10 billion solar masses. But as a population, okay, nearby quasars seem to host much less massive black holes. Now, of course, this doesn't mean that black holes are losing mass. Okay, Hawking radiation is irrelevant for such massive black holes. It only tells us that the quasar environment no longer hosts massive black holes today. Okay, another way to put it is black holes today, okay, these got to be around somewhere. Very massive black holes no longer live in a galaxy that emits powerful emission lines. You know, it's no longer gobbling up huge amount of gas and shine as a quasar today. When the universe was young, gas-rich, very high density, it was in a very active phase. So then the obvious question to ask is, where are they today? What are the descendants of high redshift quasars? What have they evolved into? Okay. And we think the primary suspect is nearby massive elliptical galaxies like M87. So from the surface, they look very quiescent, boring almost. Lots of stars in a sort of ellipsoidal potential, very little gas, very little star formation, very weak activity at the center. We don't see this quasar output. So the black hole, we think, is lurking, is still living, sleeping at the center. And the only way to infer its mass is through measurements of the kinematics of the stars, okay, or some kind of ionized gas around it. So they are relatively difficult to observe, but that's why we want to explore this parameter range, because that's sort of the missing parameter here. And of course, central black holes, for those who work on galaxy formation, know they are critical for regulating galaxies' stellar mass, color, star formation rate, so-called quenching. We need these black hole activities to shut down star formation, actually, and to do various things to the properties of the galaxy to get them right. Okay, again, this can be a whole talk by itself. A lot of people are working on this aspect, but I won't focus on that today. Okay, so hopefully I've given you some motivation for why it would be good to get more data for the very massive end of the black holes. And I have told you that more massive black holes seem to live in more massive galaxies. Okay, so then you think, okay, massive galaxies are big. Okay, these black hole masses are huge. Therefore, their sphere of influence, the region where the gravity will be dominating, is relatively big. So shouldn't they be much easier to find? Bigger things generally are easier to find. So why have there been so few measurements at this end? This was a question I asked 5-6 years ago when I started the observational project. So let me just highlight a few observational challenges and tell you just a little bit about how we go about getting the black hole mass. Okay. So challenge number one is, obviously, to infer the black hole mass, we need to get velocities of the very nearby stars, then which means angular size-wise, we need to resolve. We need to have fantastic angular resolution. Okay? But massive galaxies are rare. Okay, the mass function of galaxies falls off exponentially at the high mass end. So the more massive you go to, the fewer there are out there. So you must, in order to find them, right, these are best sites hosting the most massive black holes in the universe, you've got to go beyond our very familiar local environment, and that's probably highlighted by Virgo cluster, the nearest cluster to us. That's at about 16 megaparsecs. Okay, and there is a very well-known early type galaxy or galaxy survey that probe a volume-limited regime of 42 megaparsecs centered around us. And that volume, in fact, is a little too small to get a lot of the massive galaxies. Okay, so we would like to go to about, rather than 16 megaparsec or 40, we would like to go to about 100. That's where the next big cluster is, Coma Cluster. Okay, that volume is then quite big. And then the problem is that's where you can find a lot more massive galaxies, but then they're more distant. So I just give you some numbers for reference. Okay, so this is a rough estimate of the size within which the black hole's gravity will dominate. This is basically the radius within which the stellar mass is about half of the total mass. So the stellar mass and black hole mass will equal each other. And this is so typically called the sphere of influence of the black hole. Okay, it's about GM over sigma squared. This is the velocity dispersion of the central part of a galaxy. Okay, so if you put into a typical values for a big galaxy, even if we take very large 1 billion solar mass black hole, that size is about 50 parsecs. Okay, about 160 light years. That sounds actually quite big, but if you put this at a distance of 100 megaparsecs, that's where we will find these galaxies, right? 50 parsec, we will need to resolve. We would like to study the kinematic starts within this sphere. It's only about 0.1 arc second. And typical seeing from the ground, on a very lucky day, the best side you may get 0.5 arc second. Typically, you get 1 or 2 arc seconds. Okay, so you really need HST, Hubble Space Telescope kind of angular resolution to make this kind of studies. Okay, then sure enough, people in the past decade or more had been using the Hubble Space Telescope to study the centers of these galaxies. In fact, that's where the prior measurements of black holes in the nearby universe were obtained. Now, so what's the problem there? So here comes a second challenge, which is these very massive galaxies tended to have actually relatively shallow, low central density in stars. Okay, why this is so is an interesting question by itself. But let me just tell you observationally what's known. So this is just the surface brightness of the stars as a function of the radius from the center of each galaxy of a bunch of nearby, mostly probably Virgo, some other galaxies, okay? And these solid ones overall are more luminous. They are much higher in stellar mass, much more luminous if you integrate the light. But the dashed ones tended to be the punyr ones. But you see this different in light profile, shape of the light profile. The nuclear team like to call these core versus cusp. That's somewhat controversial, but you do see the overall trend for the very massive galaxies to be quite relatively dim at the center. Okay, some people believe that this may be actually due to the so-called stellar core scouring due to binary black holes. When they try to shrink, they do this slingshot by kicking out stars on very radial orbits. So the star carries away the energy and angular momentum, allowing the black hole binary to shrink. Okay, as a result, you lose some of these stars at the center, perhaps forming a core. Again, that's very interesting study by itself, but the observational fact is there's just less light, ironically, in the big elliptical galaxies at the center. So this makes HST inadequate because you can't get enough photons. There's not enough signal to noise to actually get from the centers of these very massive galaxies, yes.
Each line is a different galaxy.
That's right. So this is one galaxy. That's another galaxy. Okay, so this is a light profile. And so you're seeing a few tens here. But the key here is the solid ones are the more luminous ones. You integrate it out, this dominates. Okay. So in fact, larger, more massive galaxies are harder to image at the center. So then what you need is HST type of angular resolution, but bigger telescopes. And that's where 10-meter ground-based telescopes with adaptive optics, which allowed us to achieve almost HST angular resolution by correcting for the turbulence in the atmosphere. Okay, it's a fairly new technique that's now the biggest telescopes all have this kind of capabilities. Together, and we now also use, obviously you want to get spectra, you want to get the light's velocity dispersion, and we not just use a long slit anymore, but we use this fancy toys called the integral field spectrographs. So it's actually 2D spectrograph. In one shot, you get spectrum for every sort of pixel or fiber on the sky. So you get a two-dimensional velocity map of a galaxy. And that allows you to get a lot more information about the stars at the very center of the galaxy. Okay, so that's our primary approach. So this is sort of the post-HST era for studying massive black holes. Okay, so let me just introduce a few of the instruments we've been using. It's sort of a laborious process studying each black hole because we need a combination of spectroscopy and photometry. Spectroscopy-wise, not only do we want the very central part, there's some degeneracy between black holes, stars at the center, and the outer part, stars and dark matter. Okay, I don't want to go into details here, but we will actually like to get the stellar kinematics over a fairly wide range of length scales. Okay, so for the slightly outer part of the galaxy, outer part I'm still talking about, one effective radius or so, we use these, we use the virus P, McDonald Observatory in Texas. It's a huge IFU. Again, each fiber here gives us a spectrum. Okay, sort of like the Sloan's capability in the upcoming manga experiment. You can see here we don't nearly, the central fiber, each fiber is 4 arcsecond thick, so we don't have nearly that angular resolution to study what happened to 0.1 arcsecond. But it allows us to map the mass due to stars and dark matter overall very well. Okay, and I'll come back to this instrument for our massive survey momentarily. We also use Gemini GMOS north and south, which allows us to get now down. This is natural seeing. Okay, no AO, and on a very good day, we can get down maybe to 0.3, 0.4 arcseconds. Okay, and then with AO, we use both Gemini, this is 8-meter telescope, CAC is 10, NIVs, and both of these allow us to get to very, very central region. Again, this requires adaptive optics to work and everything to work, and it's pretty painful. Half the time, something goes wrong. And that's when I wish I were a theorist, or that's when I want to go back to theory. Okay, so we have multiple spectroscopy for each galaxy. And in addition, we also need fantastic photometry, the light distribution. Typically, we need HST or ground-based AO imaging in the infrared because, as I will show you, our orbit modeling to tease out the black hole mass is constrained to reproduce the light profile exactly. So that's a very important constraint. So photometry and spectroscopy. Okay, so let me just show you probably one of the most massive galaxies within the local 100, probably the most massive galaxy in the local 100 megaparsec volume. And this is the Coma Cluster you're seeing. So each one is, you see they're fairly homogeneous and boring in color because they're all mostly elliptical galaxies. Tended to be very red, very little star formation. Okay, and Coma is known to have 2 giant elliptical galaxies at its center. This is NGC 4889. That's the other one, the 4874, and they're pretty close in luminosity. This one wins, so often it's called the brightest cluster galaxy BCG. Okay, and this one really is enormous. So let me zoom in. It's just an optical image. Okay, so this is one of the galaxies we had targeted. Again, at 100 megaparsec, it's fairly distant for this kind of measurements. So what we do is we go to the very, very center of this galaxy and try to get stellar spectroscopy. Yes.
So work on NGC 4258, which has the megamasers and the accretion disk, that's a very independent way to get the mass of the black hole. And back when I worked on it, a number of years ago, there was actually a discrepancy between the black hole mass from that direct method compared to the stellar dynamics. So have you guys redone this to see if there's more consistency between this other rung, basically, of the mass ladder?
Right. That's a very good point. There are only a handful of galaxies that you can do. You have more than one tracer that's adequate. So it's adequate for this job. 4258, as you know, is one of the few amazing galaxies that actually have masers at the center. Those are very few. And the stellar kinematics is difficult for its own reason. I think 4258, in fact, now the measurements actually agree better than some other galaxies. M87, the big one I showed earlier, is one example right now. The gas and the stars give black hole masses off by more than 50%. Okay, people tended, masers are the best tracers. They are beautiful. And I will show you in my compilation those measurements. Okay, but they're far and few in between. There are maybe about 8 systems known. Then stellar kinematics probably are more robust than ionized gas. Ionized gas could be broadened, the line width could be broadened by turbulence, all sorts of things. So I would probably trust the stellar mass measurement a little, stellar kinematic measurement more. But I think it would be very good to be able to do that for more systems. Okay. And this one, no, the answer is no. This galaxy does not have masers. There is no gas at the center. It's just really, really star-dominated in black hole and dark matter. So just a cartoon picture of how we actually get the velocity distribution of stars. Okay, this is the key information in addition to the photometry we need. A lot of details going into how you actually extract from these absorption lines, okay, which is broadened by, right, a swarm of bees. Each one is going at its velocity, so there's a distribution. So the typical technique is to take some template stars that you think a galaxy is made of. They have very sharp absorption features due to whatever chemical elements, and then it's convolved with some kind of velocity distribution to get you the observation. So we usually take some template, and there are worries of template mismatch and so on. We've tested these things fairly carefully. And you know this, you put in this, you try to extract this. I don't want to go into the details, but I want to just highlight one thing is we don't just, this looks Gaussian, but we would like to get several moments of the distribution. Okay, so we don't just care about the mean, which is of course just the relative radial velocity. A lot of attention has been paid on the second moment velocity dispersion, sigma. Okay, but in fact, most of the time these distributions are not Gaussian, and we would like to get the tails. We use Hermite-Gauss polynomial, the H4 for the skewness, H4 for the boxiness of the velocity distributions, because we feed this into our short orbit code, which is complicated enough that it can use that information to constrain the various mass components. Okay, so we get these absorption lines, but standard, usually people stop at getting, they all care about is V, radial velocity, and sigma, but we actually would like to get the higher moments. And that's, a lot of care had to be taken to how to do that, what signal to noise you need, what kind of spectral resolution, and so on. But we have been trying to test this step very carefully. Okay, but for the purpose of this talk is we get something like that for every galaxy we sample as a function of spatial, right? Each fiber we get a velocity distribution. So we get a lot of information about what the stars are doing near the black hole. Okay, so let me summarize sort of so far what we've gotten and what's ongoing. So we've published 5 black hole masses thus far for 5 very massive galaxies. You see the velocity dispersion here with varying distances. And all 5, we started out choosing them to be the brightest cluster galaxies because they are some of the most luminous galaxies. Okay, but now we are going beyond this. We just want to find whatever massive galaxies are out there. So the 2 that sort of broke the M87 record are on the order of 10 billion solar masses. 4889 was the galaxy I just showed you. Okay, 3842, we got more, it's a more regular galaxy, so we got tighter bounds. And again, it's coming out to be about 10 billion, and that's quite similar to the quasar, the most massive quasar, the black hole masses in quasars at a high redshift. So it's tantalizing to say that maybe these are the dormant nearby quasars. This is what quasars have become today in these giant elliptical galaxies. Anyway, we have a lot more data in hand, and we are waiting for more data to come in for this semester. Okay, so let me just walk you very quickly for the other sort of major component of this project, which is the theoretical modeling part. Okay. So from spectra, I told you we get velocity distribution as a map, and we have photometry. So how can we best use this information to recover the black hole mass? Okay, some people may say, you may think, oh, Jean's equation, right? I can take moments of the lowest 2 moments. One can actually do a little better than that. And the standard technique is the so-called Schwarzschild stellar orbit modeling. Okay, again, there's a pretty big literature behind this, but I just want to give you a very quick sense of what this method is. It's a static, it's an equilibrium potential Monte Carlo process. Okay, you generate tens and tens of thousands of allowed stellar orbits in a potential. Okay, so there's some very good papers about this, but very briefly, okay, so this is a theoretical component that we have to do for every galaxy we observe. Is in this model, you assume a central black hole mass, which we would like to determine. And one thing you do need to assume is a mass to light ratio of the stars. We measure light, we don't know this mass, and there is one parameter, standard called m over L, that is assumed for the galaxy. Okay, and we've studied whether this could have a spatial gradient and so on. Again, that's details. Okay, and this is just a Newtonian calculation. You assume the black hole sits at the center, and then you have 2 other mass components. One is due to the star, and one is due to dark matter. Okay, and we can measure the stellar profile. You saw the surface brightness, right? We know its distribution as a function of radius. We do need to deproject this into 3D. Okay, there are some issues there, but just caveat. Okay, then we multiply, right? So this is light profile, then this gives us the mass profile for the stars. And again, you can introduce a gradient here if you want to. For these giant elliptical galaxies, looks at a mass to light gradient is not very steep at all. It may be consistent with being constant. Okay, we'll study that. And dark matter, of course, doesn't contribute so much near the center, but the slightly further out, dark matter start to dominate. So we would like to do this together. So this is when the large wide field of view virus P data become quite useful. Okay. Anyway, you assume a potential, and we usually assume an axisymmetric potential. Okay, then you can generate all the allowed stellar orbits in this axisymmetric potential, and there are many different kinds of orbits. This is a Monte Carlo method. Typically, we found maybe tens of thousands of orbits will give us a converged answer. So what you do is, and you say my galaxy, the observation is a combination of these orbits with free coefficients. Okay, so you want these coefficients to be able to reproduce, number one, the observed light profile I mentioned. So here, this is why we need the HST data so much. And then, of course, the line of sight velocity distributions we measure for different parts of the sky, as I spoke before. Okay, so for each set of parameters, we do this and determine the best set of orbits that will reproduce this. And then we repeat this over a 2-dimensional grid to see which one gave us the best fit. So this is sort of a standard output we get. So we constrain these two parameters simultaneously. Okay, this is for NGC 3842 from our IFU data, integral field spectrograph, from various instruments. And this is how we arrive at the black hole masses and mass to light ratio. People who do extragalactic astronomy, there's a lot of information one can get from the mass to light ratio, for example, the shape of the initial mass function of the stars, IMF. That happened quite hotly debated recently, that whether in these very massive galaxies, the IMF steepens at the low mass end. Okay, so, and that's intimately related to this parameter. So we can get more than the black hole mass in this exercise. But this is how we quote the results for each black hole.
So is it consistent, the mass to light ratio that you get from this independent method compared to some of Peter van Dokkum's and Charlie Conroy's work where they suggest that...
So some galaxies it is, some it's not. So there's one very interesting galaxy where it, based on this, it rules out saltpeter. So there's some tension somewhere. This galaxy just doesn't have, this is too distant for their sample. Okay, so we're trying to do the IMF part for these more distant galaxies too. Yeah, but that's a very active field of research right now. Okay, so these things all tie together. Okay, so let me now put these things together. Okay, so we are preparing a draft publishing 5 more black hole masses, and we would like to add more to the high mass end. So let me now show you the current state of black hole mass measurements for the nearby black holes that we can measure, we call it directly through kinematics of stars, or gas, or masers. These are the 3 tracers. In contrast to, say, quasars or AGNs that rely on those line, emission line or more indirect proxies. Okay, so these are probably the best we can do, and it's limited to a very nearby galaxies. So with Nicholas, we compiled sort of this scaling relation everybody was very excited about 10 years ago. So this is black hole mass. Okay, from, again, this is 4 orders of magnitude from million to 10 billion. This is sigma, the velocity dispersion of the host galaxy. There are a lot of issues about how this is measured, but again, I don't want to go into details here. This is basically the central part. Okay, it's sort of the one effective radius or so. Again, every symbol here is a galaxy. Okay, so just to guide you through it, we've color-coded the 2 types of information here. The kind of symbols label the 3 tracers I mentioned earlier. Okay, so masers are these triangles. So here is Merriam's 4250A. You can see several others that were, so this is a recent compilation, updated the 2009 Göttingen. Some of you may have seen that compilation, used a lot before. This is a major update of that plot, adding these points. So you can see the black hole mass errors is within the symbol, is a beautifully measured black hole masses. And they tended to be sitting in the lower mass galaxies. Okay, let me just move on first. And then the circles show those inferred from ionized gas. And the stars are the tracers we use, the stellar kinematics. Okay, so that's the 3 symbols. The colors code the type of galaxies. Okay, the blue ones are, we call it late type, tended to be star-forming spiral galaxies. For example, Milky Way is here. Okay, and the red and the green ones are ellipticals, early types. They're the red, dead, relatively spherical, ellipsoidal rather than disky. And we highlighted those that are bright central galaxies as green here, just to see. And several of these are our own measurements. So M87 was the previous record holder, and these are the 2 ones we obtained recently. Okay, and you can see the error bars are much bigger than the masers, but so interestingly, the amazing galaxies seem to show a huge scatter. If you just use your eye and single out the blue triangles, I mean, there are no error bars, literally, okay? Then it's due to intrinsic scatter. So we thought, okay, maybe it's time. People used to, whenever you see some kind of correlation like that, people like to fit a power law. Okay, so we tried that. So that's all 72 galaxies. The best fit power law is shown in black here. And that's our now new slope. And so those of you who follow this literature may know that when the correlation was first reported in 2002, two groups got two different power laws. One was 4, one was 5. And people went on. Each paper had been cited by, one was Gebhardt et al., one was Ferrarisi and Merritt et al. Each one had been cited more than 2,000 times. And people debated about 4 is right or 5 is right for a decade. And the reason this is important is it has implications for the feedback of how the black hole influences the gas, whether it's injecting energy or momentum into the surrounding gas and the whole galaxy formation process. So people are very interested in this power law slope. Our new latest data is showing a steeper power law than the Göttingen 09 compilation, mostly because of two things. One is our data points tended to pull a high, and the new Mazur's points tended to pull a low. Okay, so together, it's gotten steeper. We would like to advocate that these galaxies are formed very differently. Late-type galaxies, early-type galaxies, okay, spirals, ellipticals. I think we have enough data now to fit them separately. Okay, I think their formation, both the galaxy and the black holes, probably follow different routes.
Sorry, what is the meaning of the horizontal error bar, say, for the Milky Way?
Yeah, that is a very good question. In fact, we don't know the sigma for the Milky Way very well. So,
that's because it's for the knowledge.
Right, and it's very hard to measure. Okay, so this is mostly taken from Tremaine, 2002 et al., and some of them he just assigned 20%. Okay, so this is actually a big issue we are emphasizing now, that people pay so much attention to the vertical, both measurements and error bars. I think sigma actually, we need to agree a little better on, depending on the aperture you're using. Now we also have spatially resolved sigma, right? We have sigma profile as a function of radius because we have IFU data, and it's not flat. So what do you want to use as a proxy for the potential of the galaxy? Is an interesting open question. Okay. Yes.
What's the connection of this to the graph you showed before, where you had the size of the galaxy?
Yeah, this was one of the proxies she used for the mass of the galaxy. It's the same.
Right. So that was a cartoon. This is exactly the same. That was a cartoon. This is real data.
No, but why? What I don't understand is why is sigma a proxy for the mass of the galaxy?
Oh, I see. Because dispersion, GM over sigma squared GM over R. So if you measure this, typically this is measured out to half-light radius or some kind of effective radius of the galaxy. So this tells you basically the depth of the potential. Okay, so the higher velocity dispersions indicate deeper gravitational potential, larger masses. Okay, you can use other proxies. I'll show you. We use stellar masses. We use luminosity. They all show positive correlation. The power laws, of course, are.
The total mass of the Milky Way is so uncertain.
Oh yeah, believe it or not. And it also depends on out to what radius you're measuring it, right? This is typically measured within several kiloparsecs. When you go to even further out, dark matter starts to dominate. So you have to be careful that you define it carefully. Right. So the early and late types, okay, we fit them separately. We think that's the blue and the red. I think this is more sensible to use for anyone who wants to study the implications of these scaling laws for theories. I want to highlight the epsilon here. This is the intrinsic scatter. Okay, in the relation, it's defined as usual quadrature way. Basically, larger error bars will give you smaller intrinsic scatter. Okay, very tiny error bars, then to explain the differences will translate to very large intrinsic scatter. And it's interesting. So there has been a lot of debate in the literature which proxy, which relation, scaling relation is the tightest. The reason this is another reason this is useful is it's extremely difficult to get black hole masses. You've seen here, that's relatively easier to get sigma, luminosity, stellar mass, relatively. So if we can use this to infer the black hole mass, then we can do a lot of population studies of many galaxies, what their black holes are doing. Okay, so these relations are often used for that purpose. Okay, so the key here is the two have comparable. You can see the late types really had huge scatter, mostly because these Messier points are all over the map. Okay, Okay, but the amplitude is off by a factor of 2. So at the same sigma, early type galaxies now seem to host a black hole that's on average twice as massive. Okay, these are just what we can get from the data right now. Yes.
However, if you put them separately, so your late type galaxies have a mean sigma that's significantly lower than your early type galaxies, right? So
right. So you should think that that fit is only valid out to this region.
Yeah. So your individual fits are dominated by 2 different regimes in sigma.
Oh, that's right. That's right. I mean, that's just how, and that's why this is steeper, is because, exactly, yeah. So I would not try to fit this or make too much interpretation out of that particular exponent, because it's the two slopes being off, I mean, two relations being offset, that's somewhat making it even steeper. Okay, so if I show you the mass luminosity, this is again luminosity of the bulge, okay, the spheroidal part. The mass of galaxy doesn't matter, that's the entire galaxy. When you go to those Messier points, that's why people don't plot the late types anymore, because the bulge disk decomposition becomes very murky. Okay, so the late type, if you just plot the early types, it's about almost linear. And I think a more interesting relation is the black hole mass versus the stellar mass of that spherical, the bulge component. And it's consistent with being linear. Again, you can see the scatter is fairly consistent as about 0.3 dec. Okay, this is in dec, sorry. This is a little bigger. So I wouldn't say, a lot of people try to advocate M sigma being the fundamental relation. I would not say so at all. Okay, I think M star is just as tight. So let me make one comment about the scatter now. Okay, I think we can actually learn more beyond just the overall power law, which is the past emphasis. Now, I think the scatter actually is quite useful. So we have barely enough data points to bin this into 3 bins, okay, just to see, is there a mass dependence of the scatter? Does the relation tighten or gets less tight when you go to higher masses? And there are various estimates here. Just focus on this lower right panel. This is the scatter in the black hole mass versus the bulge, the last plot I show you. And these are the 3 bins we were able to parse, okay, and various ways to estimate the intrinsic scatter. Basically, we see very weak evidence for any mass dependence. That is, the relation seems to have fairly constant scatter over at least the upper 30, factor 30 in stellar masses. Now, why would I care about this? Okay, I just want to give you an example of something we think we can rule it out now based on theoretical modeling. And this is quite curious. Okay, so there have been a number of papers in the past few years. Okay, this is theoretical, and remember how I was doing song and dance about bigger black holes live in bigger galaxies. But these folks said, let's back off. Okay, start out with this blue population at some high redshift. Okay, I take a range of galaxies in my simulation, my merger trees, semi-analytic models, whatever. I put my black hole down in each galaxy, completely uncorrelated with the stellar mass of my galaxy. So I start out with a random seed. Okay, you're free to assume that. And they claim that now we do have a pretty good idea of how galaxies merge in lambda CDM universe. So they use whatever merger tree you want that tells you the probability for merging one dark matter halo with another one. Okay, so they build this galaxy up through time. It doesn't really matter what you started out with here. Okay, you can try different shapes and so on. The redshift doesn't matter too much as long as you start early enough. Through central limit theorem, they say that. So the only rule here is every time I merge two galaxies, I sum up the black hole masses that I put down initially randomly. As time went on, they got a relationship that got tighter and tighter and tighter. And because when you merge upwards, central limit theorem reduced the scatter. And this is so there's no gas physics here. Okay, so it's not realistic. This is somewhat a toy model, but merger is very realistic in this model. Okay, so their point here is the correlation tells me nothing. Okay, about the initial correlation between the two. Basically, I can statistically just generate this kind of correlation people were so excited about. But our argument here would be that we don't see this But one key prediction of this model is the scatter will decrease as a function of mass. And we don't see that in the data at all.
Is the sample that you have, I don't know enough about like selection biases of the population. Is it an appropriate sample that you can address that kind of question?
Well, it's a fair question. That's the sample we have. There are systematics. There is not an obvious systematic that's mass dependent to explain this, to say the system, we're systematically enlarging the scatter at a high mass. And all the systematics we know of kind of operate similarly. So you can say our overall scatter may be off. But I think the mass trend of the lack of mass dependence it cannot be easily explained with that systematic.
I noticed going back on the previous plot, the most mass is about 10 to the 6. There are some that are known lower, like 4395, which is about an order of magnitude lower, and that's pretty well known. Why didn't you include some?
It's not a,
4395.
well, how is the measurement obtained?
I think it was kinematic. It's a very well known, very nearby system.
Yeah, we have a black hole website now. That may be one of the ones we put in the very complicated. We've removed some of the ones that have been shown to be quite controversial. So was it number 43?
95.
Okay, I'll check it for you. 4395. Okay, what's the black hole mass?
About 10 to the 5.
10 to the 5. It's not a globular cluster. It's a galaxy. Okay.
It's an SD galaxy.
Okay. Yeah. I mean, there is a 15 or 20 that didn't make it onto the plot for various reasons.
So for this statistical, the next slide. So but there they also have to still get a number for the stars. I mean, they do that easily for the black holes, you just add it up. But for the stars, you still need to understand, if the stars, the visible stars, will be around, or if they can, what the light ratio will be for after the merger. So how did they treat that?
Oh, I see. No, it's purely sort of a game that for generating. So you can ask whether they get the stellar mass function right, and so they didn't address that at all. Their whole point is we can get the correlation through pure merger. Okay, yeah. So I mean, I'm by no means is this realistic, but it's intriguing, right? You can actually get a correlation that had nothing, that showed no initial correlation. But we would like to say that we don't think this is happening, and people would not argue so much. I mean, I think gas accretion onto the black hole is critical. Okay, so let me show very quickly again another usefulness of this local black hole scaling relations. Okay, again, I don't want to go into details, but I think this is pretty exciting. These are gravity waves in the nanohertz regime. Okay, so the primary sources for these gravity waves are believed to be supermassive black holes of the masses I'm talking about, 10 to the 8th to 10 to the 10th. Okay, and there are three international collaborations. The radio frequency, so these are radio arrays that are measuring pulsar timing. So these are 5 to 20 millisecond pulsars in our galaxy. They believe if there are some gravity waves coming from extragalactic binary merging black hole binaries, they will induce minute but correlated signatures in the pulsar arriving arrival. Okay, and these are the various. This is the new latest, most stringent upper limit from the Parkes array. This is a Science article by Shannon et al. So this is their latest upper limit on the gravity waves due to this that they can constrain in units of omega. Okay, I don't want to. There's some kind of probability. I don't want to go into details, but I would like to highlight that these various theoretical models, okay, trying to predict gravity waves due to merging black holes, differ dramatically. And a lot of these depend on how you model the black hole merger and the demographics of black holes. And one key ingredient to all these models is the local scaling relation, because you need to know when you how the black holes are populated in each galaxy. And several of these have now used our steeper slope, the higher black hole mass for a given sigma is increasing the ray somewhat. Okay, we would like to determine that scaling relation even better with our new data, more data. But you can see that some of these models are being ruled out, and there are lots of assumption made behind this. But that scaling relation is a critical input for these theoretical uncertainties. So I'm out of time, so just 2 minutes now on the massive survey. Okay, so I would like to just highlight the ongoing effort that we're very excited about. So I've shown you several black hole measurements. Now to pick those galaxies, we have been doing quite a heterogeneous selection. Basically, observing telescope proposals are due 2 weeks. We need to find some good targets, and then you see which one is a good AO targets, and those are hard to find. Okay, so we try to optimize our chances, and we've stepped back a bit, and now we have shown that this method, these telescope instruments work. We can get black hole masses. We'd like to do a survey. So we've started at what's called a massive survey. Okay, and this is to go beyond just the black holes, but and Jenny Green is a key collaborator here. Again, we would like to do IFU like what I discussed before, but we would like to have a stellar mass selected sample of galaxies. Simply put, out of the distance of Coma, what are the 100 most massive galaxies? No, okay, in stellar masses, and we would like to get 2D spectra for these galaxies, so we can study not just their central black holes, which we'll need to use follow-up AO data for, but also the whole early type galaxies. How were they formed? And why would we need yet another galaxy survey? You've heard of so many surveys, okay? But the striking thing here is you think these nearby massive galaxies are known. They're NGC somebody, okay? There's very little spectroscopy done. Even in Sloan in fact misses most of these galaxies because they're almost too nearby for Sloan to get in, okay? So most of these actually, and what's striking is it looks like there's quite a substantial subfraction of them that don't live in biggest clusters or groups. Okay, some of them appear somewhat isolated. I mean, I'm talking about stellar masses of about 3 times 10 to the 11 solar masses. This is our K-band selection, or the proxy for stellar masses. Okay, for those who think about galaxies. In contrast to the Sauron Atlas 3D I mentioned earlier, that's volume limited to 42 megaparsec. We're going out to 107 now. Okay, and we're picking, and most of these are ellipticals. And I just want to show you the parameter space we're covering, and this is ongoing. We have data for about 60% of the galaxies now. Okay, so this is just a distance to the galaxy versus the stellar mass. Okay. This is the prior Atlas 3D sample, limited to 42 megaparsec volume, right? So this is the range of stellar masses. Again, there is K-band limited, so this is range of galaxies they get. You see there are fewer and fewer at the high mass end, and 87 are nearby. Our lovely neighbor is down here. Okay. Now, when you open this up to about 17 times larger in volume, but we are now limiting ourselves, obviously there are so many galaxies here, okay? We're limiting the very, very massive end, then suddenly all these red circles showed up that were not in the Sauron Atlas survey because our volume now is big. And you can see now M87 is on the lowest end of our masses. Okay, so and put another way, there's all these massive M87 or bigger like galaxies just out beyond the Sauron's survey limit. So we are studying these galaxies, and for a subset of them, probably 30 of them, we are hoping to get black hole masses. Okay. So I skip the science goal and go to the summary. Okay. So although there are only 72 galaxies in our sample, there are a few more added now. During the process, I, for one, was starting to get confused by, this is all by different, each paper had 2 masses reported, so just to compile them was starting to get confusing. So we thought we'll put a website up just to keep track of things, and people can now look up the properties of these black hole masses and read citations and so on. So I thought, okay, I would like to have a domain name for black hole. So I looked up blackhole.net, blackhole.org, whatever you can think of, and they were all taken. Then you click on the site, most of them were blank. I think people just bought them off, thinking black hole is a cool name, and they were not they're not active sites. So I looked into it, we paid them a little bit of money, and it became a fishy game. Sometimes they want monthly money contribution, and just to use that domain name. And then I thought, the federal grant officers will not be too happy for me to use NSF money buying websites. So I came to Berkeley. So okay, why don't we just get a Berkeley site? So ideally, I would like to have blackhole.berkeley.edu. But this obviously belongs to campus beyond our department. So we found this campus web mistress. So she apparently, her job is to determine websites for the whole Berkeley. So our system manager, computer manager, emailed her saying, could we have blackhole.berkeley.edu? So she checked and she came back to us saying, sorry, it's used. It's taken. So, you go to that site before this, there's nothing there. She said, well, who could be using black hole? And then she checked, she said, oh, it's used by a campus-wide mail server. I guess they thought it was funny to have black hole, so it was taken by them. But she graciously, knowing that we're from the astronomy department, she convinced them to, alias that to something else and free this domain name up for us. They say you astronomers must have a good use for that. Okay, so these are actually black hole data now you can see. Okay, now we try to update that. So here's a quick summary. Basically, we are into the post-HST era now. We can get these more massive black holes using a different technique of ground-based IFU plus AO adaptive optics. And then now we are starting to go to this regime of 1 to 10 billion solar masses, I think that are quite reminiscent of these high redshift quasars, and we would like to understand the link better. Okay, again, the scaling relations that many people are very excited about, I think we can do more detailed studies here. And we're working very hard on the massive survey, and we're preparing the survey paper right now, which should come out in the next month or two. Thank you.
So do you think, you showed that the scatter can't be explained by merging, and I think that's absolutely true. And there's a bunch of things I think that can't be explained purely by merging. But it's an interesting question whether you think the scatter would be enough, the slope and scatter zone would be enough to sort of separate out different modes of growth. Obviously you have to track the stellar growth and the black hole growth. And do you feel like if you're just, beat the hell out of those high mass galaxies, you're going to be able to tell us what fraction of the black hole mass comes from accretion and what fraction of the stars are born late and things like that? Do you think that's, or do you think it's going to take a little more than this?
It's a good question. I mean, I think scaling relation by itself, there may be too many uncertainties in the model to say definitively, other than that toy dry merger model, that we can rule out some more realistic models, because there's always stochasticity we can put into the gas accretion and so on. However, I think the Messier subsample is a very interesting subset so there I think the challenge is how do you explain the huge intrinsic scatter. If you look at that population alone, and there's 6 or 7,
all the way out.
and you can see the sigma is very, very narrow, okay, but there's a factor of 100 scatter, and there's 6 or 7, about the final 6 or 7 amazing galaxies they got data for that are coming out soon. I've seen that plot. It's not any better. So I think the question is there, do we have a theoretical model that can actually produce such a huge scatter, okay, in the relation? I think the high mass end, it depends on what we find. Another thing I would really love to find is a tight upper limit. Some of these we just don't have robust measurements, but we can get upper limits. I would like to get an upper limit that's below the scaling relation. So I can actually point to a galaxy saying, I actually think this galaxy may not have a supermassive black hole. I think that would be another very interesting challenge for a theoretical modeling.
It's funny change because just a few years ago, we were surprised to see this relation. And now you're turning around and saying it's surprising not to see it more regular.
I think either way, now exactly, yeah. And I think one thing we learned, as in anything, is you look in more detail, the scatter starts to come in, the systematics, and I think just the mean trend, the slope by itself is not so robust. I think we should add more information into that, like the scatter is a function of mass.
So I don't know enough about the dynamics and the dynamical friction, but all those examples that you're looking at, do you know that the black holes would have merged, or is there possibilities that they're still, you know, in the process of merging and you just measured the mass of like one of the two or something?
Yeah, that's a very good question. So 62, whatever that I showed with the two actual X-ray peaks, that's a candidate, okay, for one. The ones we've seen, so there is one thing we're tracking right now is offset between where we think the sort of the peak of the velocity dispersion is from the light center. So, or there's some of these there is very fine measurements in radio emission, right? That gives you micro arc second angular resolution. They know where that point source is from the center of the light, which is presumably where the stars are. And any offset will indicate recoil. So that's a signature.
Limit on how big that, you know, the number of the things in there, the black holes haven't actually merged?
Yeah, so there are a few systems we see there is actually an offset in positions of the light center and the black hole, and we're talking about, you know, maybe fraction of a kiloparsec, obviously. But that could be because after the final merger, usually the gravity waves go out, and this was a big calculation recently, debate, whether the gravitational waves carry away angular momentum and linear momenta, right? So the remnant will recoil unless you have a perfectly symmetric system, which doesn't happen. So the recoil velocity of the remnant black hole have been updated to could be up to several thousand kilometers per second. So the question was whether you can eject one of these merged black hole out. But any kind of offset could indicate the recoil of a binary black hole. And we have some information, but we don't know if it's maybe the black hole hadn't quite settled in, or it's due to recoil after a merger. That's one thing we can't quite distinguish, but that would be a starting point.
Because that can certainly go some motion of scatter, I mean, if the assumption is.
That's correct, yes.
So we'll have reception as usual on the 6th floor, so let's thank Chung-Pei.